This lecture is on simplifying rational expressions. So, to begin with, what is a rational expression? Well, the word rational comes from the same root word as ratio. It really just means something that can be written as a fraction, more generally. And more specifically, a rational expression is an expression that can be written as a fraction, p over q, for example, for some polynomials, p and q. Obviously, we also have to have q is not equal to 0, or it doesn't work. Now, why are we interested in rational expressions? Well, they can be used to model real-world behavior. In particular, one good example is rates. Some examples of some rates: speed or velocity, for example in miles per hour, or you might have seen in physics feet per second. If we had a polynomial expression that gave the relationship as how miles change over time, we could have a rational expression with a polynomial on the top, a polynomial on the bottom, that describes the way the relationship between those two things changes. We could of course have miles per gallon is another example of a rate, or dollars per month. Rates are anything where we have the rate of which one thing is changing with respect to another thing, and so we often write that in fraction form. And what do we want to be able to do with rational expressions? Well, in this lecture, we'll simplify them. But we're also going to want to be able to, in later lectures, perform operations on them. Such as addition, subtraction, multiplication, and division. And we're also going to want to be able to solve equations that include them. So what does it mean to simplify a rational expression? Well, we just need to remember that rational expressions are just fractions. So we simplify them the same way we simplify a fraction. We basically look for common factors that are in the top and the bottom of the fraction, and we try to cancel out any common factors. So for example, when we have just regular numbers, if we had the fraction 12 over 30, we could simplify that by breaking that down as 6 times 2 over 6 times 5. And we can see that the 6 on top and the 6 on the bottom can both be divided by 6 and cancel to get 1. So we get, in fact, 2/5. 2/5 is a simplified version of what we started with, of 12/30. Well, it works the same way if we have polynomials on the top and polynomials on the bottom. We know how to factor polynomials. So in much the same ways, here we can factor out any numbers that exist in both the top and the bottom. When we have polynomial expressions in the top and the bottom, all we need to do is factor out common factors of those polynomial expressions. So let's work on some examples. For example, let's take a look at x squared minus 16 over 4 minus x. And we want to work on simplifying it. So to begin with, in order to figure out what common factors we have in both the top and the bottom, we need to actually factor. Well, we can see that the top can be written as x plus 4, x minus 4, and on the bottom we still have 4 minus x. Now at first it doesn't look like we have a common factor, but we notice that 4 minus x can be rewritten as negative x minus 4. We pull the negative sign up front. And in this case, the x minus 4 on the top and the x minus 4 on the bottom can both be divided by x minus 4 to give us 1 on the top and 1 on the bottom. So now we have x plus 4 over negative 1, or negative x plus 4, which we could also write as 4 minus x, for example. Or we could write it as negative x plus 4. And any of these are correct here at this point. These are definitely simplified. Now there is one thing we want to note. Our answer of 4 minus x is mostly the same as the equation we started with. We were able to get it by factoring the same thing out of the top and the bottom. But there's one minor difference from the case when we have numbers that we're factoring out of the top and the bottom. And that's if you notice the following. By doing this factoring, there used to be a 4 minus x in the bottom of the expression, and there isn't a 4 minus x in the bottom of the expression when we're done simplifying. That changes something. In the original expression, x was not able to be 4. Why? Because then we would get 0 in the denominator. But in our simplified expression, we can have x is equal to 0. So we notice there's a change here. Sometimes when we simplify an expression, it changes what values we're allowed to put in for the variable. And this may matter depending on what we want to do with our expression. For example, if this expression were part of an equation and we were trying to solve for x, if we got x equals 0 as one of the solutions, we'd have to rule it out, because while it might be a solution to the final equation, it's not actually a solution to the initial equation. So we have to be very careful to check these things in the instances, for example, when we're solving equations. So it's just important to be aware that when we cancel things out that contain x's, so that we remove something from the denominator, we notice that then we're removing one of the problematic values of x. And therefore we're changing the set of values that we're allowed to put in for x. And that could change our answers when we're solving equations in future. Okay, let's look at some more examples. Now let's simplify 2x squared plus 5x minus 3 over 2x squared plus 3x minus 2. Well, we just start by factoring the top and the bottom. That's the only way we'll know what common factors we can take out. The top we factor, we get 2x minus 1 times x plus 3. The bottom, if we factor, we get x plus 2 times 2x minus 1. We notice we have a 2x minus 1 on the top and a 2x minus 1 on the bottom, so we can divide them both by 2x minus 1 to get 1. And so we get x plus 3 over x plus 2 as our final simplified version. And again, of course, we just note that we can't have 2x minus 1 equals 0 in the original expression. I mean. Let's try another. What if we have 3x squared plus 3x minus 60 divided by 9x squared plus 72x plus 135. Also, we want to simplify this. Well, if we factor it out, we get 3 times x minus 4 times x plus 5. We need to factor the greatest common factor, and then factor the polynomial that remains in order to get that. At the bottom, we get 9 times x plus 5 times x plus 3. So we notice the 3 and the 9 have a 3 in common, so 3 divided by 3 is 1, 9 divided by 3 is 3. And then x plus 5, we divide them both by x plus 5, and we get 1. So for our final answer, we get 1 times x minus 4 on the top, which is x minus 4. On the bottom, we get 3 times x plus 3, which we could also write this way, if we prefer. Doesn't matter. Either one of these ways of writing is fine. And we notice that we did cancel out an x plus 5 on the bottom, so we notice that x cannot equal negative 5 in the original expression, which may or may not be important depending on what we want to do, but we should keep it in mind. Let's look at one that doesn't just have x's in it. If we have x squared minus 3x plus xy minus 3y divided by x squared minus xy minus 3x plus 3y, and we want to simplify that. Well, we would need to do some factoring by grouping, but if we do factoring by grouping, we could go ahead and factor it as x plus y times x minus 3 over x minus 3 times x minus y. And we notice x minus 3 and x minus 3 can each be divided by x minus 3 to get 1. So we get x plus y over x minus y as a simplified version. And again, we just note that it couldn't have x equal to 3. In the original expression. Let's look at another example. We have x minus 2 divided by x squared minus 4. We want to simplify. Again, we begin by factoring. we get x minus 2 over x plus 2 times x minus 2. We notice the x minus 2 on the top and x minus 2 on the bottom. X minus 2 on the top divided by x minus 2 is 1. X minus 2 divided by x minus 2 is 1. So we get 1 over x plus 2. Again, notice it's very common for students to forget to write the 1 on the top there. But remember, it's still there. That x plus 2 at the end is still in the bottom. It's not in the top, so we need to be sure that it remains in the bottom of the fraction when we're done. And again, we'll just note briefly that in the original we had an x minus 2 in the denominator, so we can't have x equals 2 in the original expression. Let's do one more. Suppose we like to simplify y minus x over x minus y. Well, we may notice that we can take one of them and rewrite it as negative 1, so y minus x is really negative x minus y. And then x minus y on top, x minus y on the bottom. We can divide them both by x minus y and get 1 over 1. And so we have negative 1 over 1, which simplifies to just negative 1. So this actually just simplified even to a specific number. But once again, we need to note that in the original expression we had x minus y in the bottom. So x cannot be equal to y in the original expression. So we've done a lot of different varied examples, and we can see that we can go ahead and simplify any rational expression just by factoring the top and the bottom, canceling out any common factors. Just being careful that when we do that, we do it correctly. And also to note that we may change the allowed values for our variable when we do that, so we need to pay attention to that as we move forward and use these techniques in order to solve equations.